Welcome to Brain Vision.
In this problem, we're going to be looking at the total power radiated by the sun. And over here we have the Earth some distance away from the sun. Actually, let me draw it a little bit closer so that we have some space to work with. This distance here between the sun and the Earth, on average, is about 1.5 times 10 to the 11 meters. And we know that the average intensity of the solar radiation on the Earth, so that's average intensity, is equal to 1,390 watts per meter squared. Now what we're trying to find is what is the power, P, that is radiated by the sun in all directions. So if we think about it, the sun is radiating this way and this way and so on, right? And so we can imagine a sphere around the sun and its energy being radiated out in all directions of that sphere. The area of the sphere then is equal to 4 pi times the radius. Why is that significant? Well, because power is equal to intensity times area. So if we can figure out what the area is, we already know the intensity, that's going to give us the power. So let's take a look at our equation for area. A equals 4 pi r. Well, r is the radius, so in this case it's the distance that the Earth is from the sun. So A equals 4 pi times that distance that the Earth is from the sun. It's the radius of this sphere. Plug that into your calculator, and you're going to get about 2.827 times 10 to the 23. Sorry, this is radius squared in units of meters squared. So that's the surface area of an imaginary sphere, the size of the distance from the Earth to the sun. So this is where the sun's energy is being radiated out towards. Now we can use that area and plug it into our equation over here for power. Power equals that intensity, 1,390 watts per meter squared, and the area, 2.827 times 10 to the 23 meters squared. Plug that in, and we'll see that the power is about 3.93 times 10 to the 26 watts.